All right, last section. Can you believe it? I think you've been waiting for this to come for quite a while. This is all I know. No, I'm just kidding. This is all I'm going to be telling you. So, boy, you hung in there, and I'm proud of you. This is a lot of work. I understand that. I've been a student myself forever, and I understand how frustrating and difficult it can be. But how proud you can be of yourself when you're done and you stick it out and you do it and you get a decent grade and you're like, wow, I did that. So good for you. All right, so 12.5, we're going to be solving, okay? Solving for x. That's always kind of, you look at the basics and you look at all the properties and then you solve at the end, okay? I'm going to be showing you some more properties of logarithms that we're going to have for this section. But so far, we've seen the addition and the subtraction turns into multiplication and division. And I'm going to also show you, well, I'll show you a lot of stuff in here. I know it's only 8 points, but there still is quite a bit. All right, so let's just start solving for x. We have 5 to some power is equal to 25. Well, boy, that's really a tough one, isn't it? 5 raised to what power gives me 25? Yeah, I guess it's got to be a 2, right? I can also write this as 5 squared is 25, so x has to be 2. Okay, so these first two are really straightforward and easy. Very easy to solve. Not that one. The point of this is, and I have to sneeze. The point of this is, what if I had 5 to the x is equal to 26? Well, what do you do with that? Okay, there is no even integer that I know of. There's a number somewhere between 2 and 3 that's going to be this value. Okay, so how do I find that? Okay, so far in problems 1 and 2, it's very straightforward and we've got a nice solid whole number here. But what if we have an ick number in here? That's the point of this lesson. Okay, so let's start on this one. This one I think turns out to be nice and easy. All right, so I'm going to pretend like I'm solving for z. Well, I am solving for z, but I've got 4 to the z power, so it's kind of like if I had z plus 7 equals this. What would I do here if I was just solving for z? Well, I would subtract a 7 across, wouldn't I? Well, I'm going to do the same thing here. Nothing's changed. Even though it's not a z, it's a 4 to the z. It doesn't really matter. Okay, so I've got 1031. I'm going to be nice and lazy today. Minus 7. I've got 1024. Now the first thing I'm going to check for is a nice whole number in the z spot. 4 raised to some power is going to be 1024. I think that's a nice perfect. Is it 6? No, is it 5? I don't know what it is. Yep, it's 5. All right, so z has to be 5 because 4 to the z is equal to 4 to the 5th. So therefore, z has to equal 5. Okay, so when they turn out to be nice and neat like that, very easy and straightforward. So you always want to check for a nice whole number first. Now, do you think they're all going to be like that? Well, nope. I mean, look at this one. E to some power is equal to 27. Well, what's E? E is 2.7, blah, blah, blah. Okay, so this is not a nice, easy problem. If I took e to the x, and let's say I raised it to the 3rd power, I get just a little over 20. And if I take e to the x and I raise it to the 4th power, I get over 27. So I get under 27 and over 27, so my answer's got to be 3 point something. I've got 2 decimal places. I can't possibly start hunting around for that with 2 decimals, okay? It's 3 point something something, and I have no idea what it is. Okay, so here's where we're going to have to start using some other rules, all right? Well, a rule of algebra says that I can do anything to the equation that I want, absolutely anything that I want, as long as I do it to both sides. Okay, I mean, I can add 2 to both sides, I can divide by 2 by both sides, I can do whatever I want, anything that's going to help me. As long as I do the same thing to both sides, I'm cool. Well, I can also log both sides. Okay, that's doing something to the equation, and I can do the same to both sides. So what I'm going to do on this one is I'm going to randomly choose to take the natural log, and it's not really random, but I can do whatever I want. I'm just going to take the natural log of both sides. Okay, as long as I do it to each side, I'm fine. All right, now I need a rule. I need another property of logarithms. Okay, and the property of logarithms says that a log, now this is again a generic log, this could be a log base 10, log base e, or log base anything, all right, of x to the a. Okay, so whenever I have a base with a power on there, this is exactly the same as a times the log of x. Okay, so this is a log base b, meaning any base. All right, so let's prove to ourselves that that works. Let's take the common log, because I can. Let's say that I take the common log of 4 raised to the second power. I don't know. I'm just making something up. Should be the same as 2 times the log of 4. And it is. So these, you know, anytime that you have these rules, they should work for absolutely anything that you choose. Otherwise, it can't be a rule. Okay? So this is a very useful rule. This is called the power rule. That if you have something raised to a power, you can always drop that down. Do you see how what that does for me up here is it takes my x, which is in the exponential spot, and it drops it down to a normal spot? That's what I want, because I can't solve for it up here. All right, so using this rule, this power rule, this piece of it on this side is the same as x times the natural log of e. Now I can solve for x, because it's no longer in that exponential spot. Okay, x times something, well, how do I solve for x? I divide by that something that I don't want, right? Natural log of e, that's just a number. Natural log of e divided by natural log of e is gone. So I have x is equal to the natural log of 27 over the natural log of e. Nice. Well, what is the natural log of e? The natural log of e is 1. That's kind of nice, because now if I take the natural log of e, I don't even have to divide through by this, because it's 1. Anything divided by 1 is itself. So really, this is equal to the natural log of 27, which is, the natural log of 27 is this. Okay, we have 2 decimals. Remember we said it was between 3 and 4, and it is 3.3, right? That's rounded to 2 decimals. I would never have known that. Now, how do I check to see if this is correct in a test situation? Well, you check it, right? You're going to do e to the 3.3 should be close to 27. Now, this is not accurate. Look at, you know, how many, this is a very rounded answer, so it's going to be close to 27. You're not going to hit 27 on the nose there. So if I raised e to the 3.3 power, I have to get something close to 27, and I do. Now if I put in 296, I'll get it even closer, right? 3.296, and the more decimals I put in here, the closer it's going to get to 27. See, that one's a lot closer, because this is a lot closer to the correct answer. So all of these can be checked by putting the answer back into the original equation. I didn't do this one. I didn't check that one. I should probably check that one. So I have 4 raised to the 5th power plus 7. That one works. All right. I have 5 times 10 raised to some power x plus 2 is equal to 26. Okay. Again, this is going to be a nice messy one. And you know what I mean by nice. Nice and messy. It's the way that I like them, but I don't like these. I don't like problems like this. They're just doesn't really do anything. Shows you what we're doing, but all right. Let's say I had 5 times x. Again, I'm going to pretend that that whole mess on the inside is just the x. What would I do over here? 5 times something. 5 times something. Well, I would divide by 5, wouldn't I? To get that something by itself. Same thing here. Okay, what I want to do is I want to isolate the piece that's got the x on it. Okay, I want to isolate the power. So now I have 10 raised to the x plus 2 power is equal to 26/5. All right. I don't want to do 26/5 at this point because look at what oh well, okay, 5.2. If it's a lot, all the decimals, like yeah, I have to keep writing the decimals over and over and over and over, and I don't want to do that. Okay, just leave it as 26/5. All right. Now I'm kind of stuck, aren't I? And when I say I'm stuck as an exponential. This is an exponential problem that I couldn't possibly know. 10 raised to some power is going to give me 5.2. I have no idea what that is. All right. So I'm going to turn this into a logarithm so I can take this piece down using my power rule. Okay. So last time we took the natural log of both sides. This time I'm going to take the common log of both sides because it doesn't matter. So I'm going to transform this into common log of 10 x plus 2 is equal to common log of 26/5. Okay, so this is the piece that's inside, you know, that's what you're logging. So I took the log of both sides. Like I said before, as long as I do the same thing to each side, I'm fine. I can't take the log on this side, base 10, and the natural log on this side. That's not the same thing. But I can either do natural log and natural log, or I can do common and common. Okay, so now I've turned it into a log. Now I can use this log property, this power rule that says that this a piece can come down. Well, that's very useful because then my x turns not in, it becomes not an exponent. See what I'm doing? I'm using that rule to my advantage. So this x plus 2 drops it down, so it's not in the exponential spot. Now, why did I choose the natural log up here? Because the natural log of e was 1. Why did I choose the common log here? Because the common log of 10 is 1. So this is just a 1 again. So anything times 1 is itself. So that's just going to help. So now I have x plus 2 is equal to the common log of 26/5. Solving for x, I would subtract 2 from both sides. So I have x is equal to the common log of 26/5 minus 2. This 2 does not go inside there. Okay? All right, so we have the common log of 26/5, close the parentheses, subtract 2. Okay, give me negative. Negative 1, how many decimals do I need? 2 decimals, 28. 28. Fantastic. Now in a test situation, what would you do? You would put negative 1.28 in right there. And you would see how close you get to 26. If you're close to 26, if you're just under or just over, you're fine. If you get an answer of negative 2, not fine. So let's try it. So we have 5 times 10 raised to the parentheses x, which we said was negative 1.28 plus 2 power. Okay, we're just putting our answer in there now. Again, this is a rounded version, so we're not going to hit 26 on the nose, are we? No, we're not. But we're pretty close. We've got 26 point something. We're just over. So the more decimals that I put in there, the closer I would get to 26. Okay, so if you're in a test situation, I would definitely check them. I'm not going to give you an accurate, for sure, 100%, but boy, it's pretty close. All right, should we do this one? I only have 8 problems on here. I probably should do all of them for you. Plus, this is the very last lecture. This would be a fine time to get lazy, huh? All right. Again, this is your y term. It's the same as if you had y minus 9 is 16. What would you do on this? Well, I would add a 9 across. Same thing here. Okay? So we have 4.6 raised to the 3 times y power has to equal 25. Okay? This time I can add those with a nice whole number. Now again, I'm stuck exponentially. I have no idea what 4.6 raised to some power is going to be 25. Okay, so I'm going to log both sides. Now, the first time that I did that, I had an e, so I wanted to choose ln, so I got that wiped out to a 1. The second time I was working with a 10, so I wanted to log, because that was again a 1. And now I have a 4.6, so it really makes no difference. It's going to be a mess either way. Okay, so I'm just going to randomly choose the common log. It doesn't matter. So I'm going to take the common log of both sides. 4.6 raised to the 3y power is equal to the common log of 25. Okay, just as long as these are the same. Now I'm going to use my power rule because I've got that. That only applies to logarithms. That's why I log it. That drops down, so I've got 3 times y times the log of 4.6 is equal to the log of 25. All right. Now I'm solving for y. All right. I've got 3 times y times the log of 4.6. How do I get rid of times, times, times? I divide. I want to divide by 3 log of 4.6. This 3 is going to be gone, and this is going to be gone. And all that's left is the y. Both sides. Okay? All right, so now this is just calculator work over here. Once I've isolated my y. So I've got the common log of 25. Close your parentheses. And now you want to divide by. Now here you're dividing by a product. Anytime that you divide by a product of things, you have to have a parenthesis containing the entire denominator. Okay, otherwise you get the wrong answer. So here we have 3 times log 4.6. You want to close the log parenthesis, and then you want to close the denominator parenthesis. Okay? Points. Okay, so what do we need here? How many decimals do we need? Thousands. So we need 3 decimals. Okay, so we have equals 0.703. Well, before we do anything, before we put it in here, let's check it here. So we would have 4.6 raised to the 3 times 0.703 power. And we're going to see how close we get to 16. Then we have to subtract the 9. I was going to say that's not correct. Then I could have done it all in one shot. Pretty close to 16, 15.98. That's pretty close. Okay, so that's probably the correct answer, 0.703. Yep. But like I said, in a test situation, you have no idea whether you've got the right answer. So yeah, I would check it. You could also just do that. I just spaced that out, but you could also just do it all in one big shot here. 3 times, I just hit the equal sign 1 second too soon, 0.703, and then close and then subtract the 9. Okay. All right, so that's how those work. All right. So far what we've seen These are all been exponential. Look at these types of problems. Okay, I want to go back. These are all exponential problems, right? The exponential thing to do when you're stuck exponentially is to turn it into a log. Then you can see how these are all exponential problems? Look at this one. This is starting out with a logarithmic problem, right? So 6, 7, and 8 are all logarithmic problems, and we're stuck logarithmically. So what would we do? Well, when you're stuck logarithmically, you change it into an exponential. Okay, so you're always changing it into the form that you don't have to see if that helps you. Now, let's go back into our exponential to logarithmic conversion. I don't know what I had for letters last time, so sorry if they're different, just change them. So this is b to the a is equal to x. I know that I had a c in there somewhere, but it doesn't matter. B to the a is x. This to this power is this. Okay? These are exactly the same, remember? Okay, so I'm going to take my problem up there, and I'm going to for sure put my base in there to remind me what it is. If there's no base there, it's got to be a 10 because we don't have an ln, so it can't be an e. All right? So this is really the same problem as what we have. And I have no idea what this is. The log of base 10 of something is 6. I don't know what it is. Okay, so I'm going to turn it into an exponential by saying this is the same as 10 to the 6th power is x, right? 10 to the 6th is x. Well, this I can do. That I can do in my calculator. 10 to the 6th power. Come on. Is a million? All right, I can do that. Can I check it before I do that? The log of 1, 2, 3, 4, 5, 6, the log of a million is 6. So it does work. Okay, you can always check it. 1, 2, 3, 4, 5, 6. Good job. Okay, so the moral of the story here is whatever, you know, if you're stuck this way, you're going to log both sides to turn it into that. If you're stuck this way, you're going to turn it into an exponential and solve it this way. Okay? Log base 4, let's see what we have here. Log base 4 of x is equal to 2. Well, again, I have no idea. I don't even have a log base 4 button. Okay? So I will turn that into an exponential and see if that's easier to solve. So I'm here, I want to go here. So that means 4 to this power is x. 4 squared is x. Well, look at how easy that is. What is x? 16. 4 squared. So what this is saying is log base 4 of 16 is equal to 2. Well, how can I check that in my calculator? I could do the change of base, right? Log of 16, common log, over the log of 4, right, has to be equal to 2, and that's the question. Well, let's try it. I can always use the change of base formula when I've got my answer to see if, indeed, I've done it correctly. Yep, it works. 2. I can't check it with the log base 4 because I don't have that button, but I can always use my change of base formula to see if that's not the answer. It was 16. If that works. Okay, one more. All right, so now I have 7 ln 4z plus 5 is equal to 49. Okay? I'm going to want to try to isolate my log. So the first thing I'm going to want to do, since that's multiplication, is I want to divide through by 7. I don't want that there. So now I have the natural log of 4z plus 5 is equal to 7. All right, I want to put my base in because I have to change it over to an exponential. My base on an ln is always e. So this is saying as an exponent, okay, we're going to change the form. E to the 7th is this. E to the 7th is this. Okay? I'm using this. This raised to that power is that. This raised to that power is that. Well, now this becomes such an easy problem to solve, right? We're just solving for z. Okay, so you would do exactly what you would do in a normal problem. E to the 7th is just a number. It's a messy number. But we're going to subtract 5. So this is minus 5 is equal to 4z, right? 5 minus 5. And then I would divide through by 4. So here z is equal to e to the 7th minus 5 over 4. Let's get a number on that. We have e to the x, and the x happens to be a 7, minus 5. We want all of that divided by 4, right? 272.91. Checking it. I want to put that in right there. So I have 7 times the natural log of 4 times 272.91 plus 5. I lost my spot there. And that's got to be close to 49. Ooh, it is. Really close to 49. So since that's working out pretty close, I can be pretty certain that that's the answer. I always like to give you guys, if there's ever a way to check, always check. All right, so that's it. You don't have to listen to me blather on anymore. How wonderful is that? I don't have to listen to myself blather on anymore. That's even more wonderful. So yeah, that's it. That's the whole course. It's been really a pleasure teaching you guys. I prefer face-to-face just because I don't know who you are, which I don't particularly care for. But I hope to see you guys in some classes, college algebra of mine, or pre-calc, or whatever it is that you're, or stats, or wherever you're going, cultural math. I teach it all, so I hope to see you in the future. Best of luck on the final. You've got the final review problems, which is your guide, and I have taken those problems for your final. I think there's 30. Yes, 30 problems in your final exam. So not bad. It's just kind of a smattering of everything, a little bit of everything, but you've got your notes to use, you've got a calculator to use, you've got, be organized. The time limit I think I put on there is 3 hours, so I've given you plenty of time. And I will see you on campus. Take care. Thanks for taking the class.